Hello, welcome to the videos of Chapter 19 of the Crystal Clear Electronics 2 curriculum. In the previous two chapters, you have been introduced to DC motors and the basics of control engineering. Now, we will look at these topics in practice. We will be implementing speed control of a DC motor. The author of this chapter and also the presenter will be Adam Szabó.
I also welcome everyone, and thank you, Bence, for the introduction. If you've skipped chapters 17 and 18, or only vaguely remember them, please scroll through them because this topic will be based on them. Control theory and control engineering is a complex and challenging discipline. Understanding and mastering it in depth would require a university-level knowledge of mathematics, so we'll just scratch the surface.
But in the following videos, we'll show you that you can implement simple closed-loop controls without profound mathematical knowledge. Let's get started. Engineering tasks always start by defining exactly what you want to achieve. This is called a requirement specification. In this case, it is as follows. We want to set the speed of a gear drive connected to an electric motor to a value using a microcontroller while the drive shaft is under a randomly changing load.
Do you have any hints where such a speed control is used in everyday life?
To take just the most common examples, you have the checkout conveyor, which runs at a given speed regardless of the weight and the quantity of goods on the belt.
For example, escalators and moving walkways operate at a constant speed, regardless of the number of people on them.
Cooling fans for CPUs and GPUs in PCs and laptops have their speed controlled by the system to ensure quiet yet effective cooling.
Or take the cars with cruise control. These maintain the wheel rotation speed set by the driver, regardless of the road conditions or wind.
Let's look at household appliances. Newer inverter washing machines spin at the same speed regardless of how much clothes and water they contain.
Also, modern inverter air conditioners, heat pumps, and refrigerators control the compressor speed according to the cooling demand for efficient energy use.
Or, for example, the wheels on robot vacuum cleaners are speed controlled, which helps them to map the rooms they are cleaning accurately. In addition to these everyday applications, speed and position control are widely used in robotics, manufacturing, and industrial machine tools.
As you can see, there are many areas where precise speed control is needed. In our practical example, we will do this by simply controlling the speed and then examine the limitations of this. Then, we will solve the same problem with a P controller and then a PI controller, where we will see the huge advantage of the closed-loop control over the open-loop control. To get started, let's set up our system to make the task more manageable. To do this, you will need the following tools: a Nucleo F446 development board, breadboard with buttons and display, a DC motor with encoder and gearbox, motor controller panel, a 5-volt power supply, some jumper wire, and a small screwdriver to connect the wires. You can find the detailed wiring description in video 4 of chapter 17. If you have followed the videos in order, you have exactly this assembly. If you have taken the circuit apart since then, skip back to the previous video and reassemble it.
You can also use a converter like this to connect the power socket, plugging the power socket into one side and attaching the wires to the other side with the screw terminals. Always check the polarity of these converters. Although this converter is marked with a symbol indicating which part of the terminal is positive and which is negative, we do not know whether the manufacturer has marked it according to the central negative or center positive convention. It is therefore best to measure with a multimeter.
Before applying power to the panel, be sure to check that the wiring is correct, especially the display. Incorrect wiring can damage your equipment. Now, let's review what the concepts introduced in Chapter 18 mean in this example. First, let's start with the concept of a system. In this case, the whole physical system is composed of the following parts: power plant, electricity transmission and distribution network, the electrical panel of each home, the breaker box, wall socket of 230 volts, 5-volt power supply, Nucleo development board with microcontroller, its PWM output and encoder input for the speed of the motor, motor control H bridge, electric motor unit with our permanent magnet DC motor, fixed gearbox, and our Hall sensor encoder and the load itself on the shaft.
As an introductory example, consider a speed control problem. Open loop control, in simple terms, is about giving commands to your system without checking the result of their execution.
Think of it as trying to walk through in Super Mario with your eyes closed. To do this, you need to be very familiar with the system itself, in our case the arcade track, and you also need to know exactly what will happen as a result of each of your actions, meaning pressing the button on the computer. In the case of an electric motor, this means that we need to know exactly how the motor behaves and reacts to different inputs. To do this, we need to create a model of our system.
The model is a simplified representation of our system, which allows us to omit features that are not important or significant to us.
However, care must be taken to keep all the necessary parameters. If we leave out an essential part of the system from the model, our model will no longer describe the actual system, and our final result will be wrong. Each part of the system mentioned here has its own properties, operating parameters, and limitations. If we want to take all these into account, our model would be very complicated. This figure shows a general open-loop control chain. It's very important to note that by model, we mainly mean only the model of the controlled system. The controller itself and the sensors are not included. In control engineering, the controlled system is called a section. So, we will now model this section. The rest of the control chain will be discussed later.
When creating the model, the previously written requirements list is a great help, as it describes the task to be carried out and shows what we definitely need. What is this specification about?
We want to set the speed of the geared drive connected to an electric motor to a value we specify using a microcontroller with an unknown load on the drive shaft.
So an electric motor should definitely be included in our model.
That's true. We also need the gearbox, because we don't want to set the speed of the motor, but the output speed of the gearbox. In this simple case, there are no more elements in the model.
We will neglect, for example, the power generation limit of the power plant, which can be thousands of megawatts, the losses of the electrical distribution network, the current limit of our circuit breakers, and even the power limit of our 5 volts power supply. The reason is that our low power motor is not capable of maxing out these power sources and power converters.
Modeling not only simplifies the system, but also describes its operation mathematically. Here, without further derivation, we assume that the following relationships hold for the terminal voltage and torque of a DC motor, where U is the voltage of the motor terminal, RA is the resistance of the motor winding, I is the motor current, K phi is a motor-specific constant, omega is the speed of the motor, and M is the motor torque. In other words, the terminal voltage of a motor is the product of two terms. One is the resistance of the winding multiplied by the current, and the other is the motor constant multiplied by the speed. The motor torque is the product of the multiplication of the motor constant and the motor current. In reality, the equations include the mechanical inertia of the motor, as well as the sliding bearings and coal brushes. Only a part of the torque will be used to accelerate the external load. The remainder will cause a change in the speed of the motor rotor. For high dynamic control, where relatively large changes must be achieved accurately in a short time, low inertia motors are specifically designed. In this chapter, the inertia of the motor and the mechanical dynamics of the system are neglected and not discussed in order to concentrate more on the open loop control and closed loop control itself. In an ideal motor, the winding resistance is 0, so the terminal voltage formula is simplified. Here, we see that the speed and the terminal voltage of the ideal motor are directly proportional, and the proportionality factor is the K phi motor constant. This parameter refers to the strength of the magnetic field in the stator of the DC motor. K is a multiplication factor derived from the motor design, while phi represents the magnetic field flux, meaning indirectly the strength of the magnetic field in the motor. It's important to note that this motor constant is only a nearly constant value. The higher the load on the motor shaft, the lower its value becomes.
If we are not talking about a motor made of a superconducting material and cooled below -200 degrees Celsius, we must count with the resistance of the winding. In the datasheets of motors specifically designed for control systems, in addition to the winding resistance and inductance, this K-phi value is also given by the manufacturer in volts per second or Newton meters per ampere. If this value is not given, it can be estimated from the idle speed.
The datasheet of the motor gives a lot of important information, much of which should be considered when designing an open-loop control. The motor is usually connected to some kind of gearbox that matches the motor speed and torque to the system speed and torque. Some manufacturers sell motors with a built-in gearbox, but often we must fit it separately to the motor. The gearbox also comes with a datasheet where you can find, among other things, its gear ratio and operating parameters. The engine we use is available with a gearbox and the gear ratio is 120:1, which means that while the motor shaft turns 120 revolutions, the gearbox shaft turns only 1, which is called speed reduction or torque boost ratio. In the datasheet, the data is given for the gearbox shaft, which must be converted to the engine shaft. This means that the given speed values must be multiplied by the ratio, while the torques must be divided by the ratio. This gives the following values without shaft load. At idle, you can expect 7,200 RPM and 0.14 amperes of current draw at 3 volt terminal voltage and 19,200 RPM and 0.17 amperes of current draw at 6 volt terminal voltage.
Note that at idle speed, when there is no external load on the motor shaft, the current draw is almost the same at much lower speeds. This is because the DC motor has significant losses in the coil brushes and commutator, and the internal friction of the gearbox is also significant. This power loss must be fed into the system at low speeds for the motor to rotate at all.
The datasheet of the engine we use does not include the engine constant K-phi, so we have to estimate it ourselves. As a first approximation, consider our motor as ideal and estimate the motor constant. To do this, we use the relationship we have just learned, which states that ideally, the terminal voltage of the motor is equal to the motor constant times the speed. In this case, always use the highest given voltage-speed pair. We need the RPM in radians per second, so we need to divide the RPM by 60 and then multiply by 2 pi. This gives us that 6 volts equals K-phi times 2010.6 radians per second. If we rearrange this, we get that the motor constant is 0.002984 volts per second.
The constant K-phi is used in control engineering, while in the world of hobby electronics, the motor speed constant is the more commonly used value, which is expressed in another unit, RPM per volts. The speed constant is usually referred to as kV and indicates the idle speed of the motor at a given terminal voltage, which is easier to understand in everyday life than the meaning of K-phi.
The motor speed constant can be calculated using the motor constant K-phi, but it can also be obtained by dividing the maximum speed, which is 19,200 RPM, by the maximum voltage, which is 6 volts. In the figure showing the general open-loop control chain, you can see sensors, but for simple open-loop speed control, we do not need sensors because the motor speed is nearly proportional to the terminal voltage of the motor, so we only generate the control signal from the set point.
One more unit we haven't talked about is the controller.
The controller's task is to generate the controller output signal based on the given set point and, if necessary, based on the sensors. By controller, we do not only mean the logic itself, which determines what signal should be output of the plant, but also the unit that produces a signal capable of working from the logic signals. This is usually called an amplifier or output stage. In electrical devices, it is some kind of power electronics, in our case, a motor driver circuit. Considering this, we can modify the overall control chain to suit our setup. Let's start at the beginning. We have a default signal that we have set, and the controller makes decisions based only on that. To implement the control block, in our microcontroller we will store the parameters that are calculated when modeling the motor. These will be used to determine the PWM duty cycle at which the motor will rotate at the required speed. The logic PWM signal is amplified by the H bridge of the motor controller.
To achieve this, the motor controller needs an external power supply provided by the 5-volt plug-in power supply. The signal amplified by the H bridge is the actuating signal, which is connected to the section. As previously mentioned, the section consists of the DC motor and the gears.
The load is applied to the motor shaft, and the figure shows that the controller has no knowledge of the load because we don't use sensors, so the actual speed of the motor will only match the speed required by the reference signal when no external load is applied. There will always be some load on the motor shaft, for example due to friction between the bearings and the gearbox.
Let's create our first simple open-loop control software. The motor speed will be controlled by the PWM signal. How to do this was discussed in detail in chapter 17, so if you don't remember it, it's worth revisiting that chapter.
As in the previous chapters, the example codes for the Nucleo F446 board used here can be found on the Crystal Clear Electronics 2 website. The link is in the description.
Load the project called Lecture 19 OpenLoop into the development environment, then open the files core/includes/motor.h and core/source/motor.c. The functions for handling the motor are pre-written here for the motor controller we use.
The motor.h file contains constants, global variables, and function prototypes. Here, for example, we can use the motor supply voltage and motor RPM at supply voltage parameters to specify the value of the supply voltage and the idle speed of the motor in the event of a supply voltage. From these parameters, the controller will calculate the PWM signal to be applied to the output to achieve the desired motor speed. Or, for example, here we can also specify the gear ratio on the motor with the motor gear ratio parameter. Scrolling down, we find global variables, such as motor PWM duty, which stores the duty cycle of the PWM signal on a 16-bit wide memory area, where 0 corresponds to 0% duty cycle and 65,535 to 100% duty cycle. Then, you can find encoder speed RPM and output speed RPM variables. The first shows the speed measured by the encoder on the motor shaft, and the second shows the speed of the output shaft of the gearbox. We do not need the encoder to implement the control, but we will use it for verification purposes so that we can get a more accurate picture of what speed set by the base signal actually is.
Now open the main.c file and scroll down to the HMI init code after the peripheral initialization. This function will do the display and button setup, and then the motor init function will do the initial setup of the motor.
In the while1 infinite loop, we first update our base signal with HMI update ref speed function based on the position of the push buttons, and then use motor set output speed RPM function to set the corresponding PWM signal. If we open the definition of the function, we can see that here we are only performing simple calculations, multiplication and division, based on the parameters given. We are not measuring anything. This completes our control, after which only the HMI update chart and HMI update display functions for showing the data on the display are run, and after 100 milliseconds, our loop starts again.
Load the example code into the development board and see what is on the display. Below the motor label, we will see the following values. The ref RPM, the speed set point set with the buttons. The out RPM, the motor speed is measured indirectly by the encoder. Enc RPM, the motor speed is measured directly by the encoder. And the encoder position, the position measured by the encoder. The purpose of the open loop control is to ensure that the out RPM, that is the controlled signal value, is always equal to the ref RPM, that is the set point value. Let's see how well this has been achieved. On the right hand side of the display, you can see a graph showing the motor speed changes over time.
Press the right button twice. This sets the reference to 40 RPM and the motor starts to rotate. In this example, the buttons work as follows. The left and right buttons decrease and increase the value of the set point by 20 RPM, while the top and bottom buttons change the value of the set point by 1 RPM. And the separate button on the far side allows you to reset the set point to 0. Step the set point with 20 RPM. You can see that the output speed is much lower than expected. If we set it to negative, the motor will rotate in the opposite direction, but we still observe the same thing. This can be corrected by calibrating the motor parameters. First, measure the maximum speed of the motor. Set the set point to a value high enough, for example 200 RPM, where the output RPM no longer increases, and then read the encoder RPM value showing the motor speed. In our case, this value is 9700 RPM. Then, using a multimeter, carefully measure the motor terminal voltage at the green terminal. Now we have measured 3.22 volts.
In motor.h, change the original values to the measured values. Upload the modified software and take some measurements. Record the speed of the unloaded motor under different set points. For example, set the set point to 20 and record the speed in a table. In this case, it is 0 RPM. Increase the set point value by 20 and record the RPM again, which is now 33-34 RPM.
If we continue this and also calculate the value of the error, we get a table like this. The value of the error is the deviation from the set point, meaning the error value is obtained by subtracting the speed from the set point. The first thing you may notice is that there is some error at every RPM, and the amount of error varies. Furthermore, we can see that the maximum speed of the system is around 80 RPM. Even if we set a higher set point, the motor cannot rotate any faster. This phenomenon is called system saturation, which occurs when some physical limit is reached. In this case, the motor gearbox pair with the 5-volt power supply can reach this maximum RPM.
That's all well and good, but so far the motor has only been tested at idle, without any additional load. Let's see what happens when we load the motor.
There are several ways to load the motor, for example by winding a thin thread around the engine shaft and hanging a weight on the end of it, or by mounting a small pulley on the motor shaft that you can break with your hands. But if you don't have any extra tools, you can load the motor with your bare hands. In this case, however, it is advisable to set the motor to a lower speed so that it cannot accidentally cause damage. Set the default setting to 40 RPM and then load the motor.
We are surprised to find that the one line showing the motor speed is actually not 1, but 2. One line shows the set point and the other line shows the actual motor speed.
Notice that the load has caused the RPM to drop significantly, from 34 to 5 to 10 RPM, but it can drop as low as 0. During testing of the example program, we found that in no load condition, our motor maintained the speed set by the set point after calibration nicely with a smaller error. However, under load, for example when the shaft was held down, the speed decreased. This is because the controller does not know the load magnitude and therefore cannot calculate with it. This could be improved if we could somehow measure the load on the engine shaft. We can do this with a torque cell, but such equipment is expensive and sensitive. From the equations of the motor, it is clear that the load torque is proportional to the motor current, so we can estimate the load itself by measuring the current. By adding this extra input to our controller, we can create a better solution to the problem.
It follows from the theoretical design of the open loop control, and we have seen that our control can only be sufficiently accurate if the parameters of the model are not only calculated but also measured accurately. This often requires expensive instruments and can be time-consuming. In addition, it may be necessary to extend our model using additional relationships and inputs to make the operation more accurate, which may complicate the control beyond a certain level.
In this video, we've learned about the theory of open loop control and put it into practice. In the following video, we'll examine how it works and what makes a closed loop control different. Stay tuned until then. See you.
Bye.